Okay, so now in this lecture, we will talk about mixed integer programming solvers. I didn't put exactly mixed integer linear programming or mixed integer nonlinear programming. In what I'm talking about here are those solvers like Cplex and Groovy, who started as mixed integer linear programming solvers. Now they have more general capabilities like mixed integer quadratic or mixed integer nonlinear. The goal of this lecture is to give you some practical idea of how the mixed integer programming solvers work. We've talked about some algorithm to solve mixed integer programming, like branch and cut, cutting planes, and so forth. But to build a solver, it's definitely more than just some theoretical understanding of the problem. Right? So what's inside the box of the solver? Right? There are a lot of engineering effort going into building a mixed integer programming solver. Okay. So just a little bit history of MIP solvers. One of the earliest solvers was Cplex. It was originally developed by Robert Bixby. He's a sort of very well-known person in this area, and it was sold commercially to what is called Cplex Optimization Inc. It was later acquired by Alloc and later acquired by IBM. So now IBM owns Cplex. But unfortunately, IBM is no longer interested in Cplex, so they are not further developing Cplex. At this point, very few people are still using Cplex because there were basically no developers for Cplex nowadays. It is still a good reference because the documentation of Cplex is very comprehensive. It's probably the most comprehensive commercial solver you can find. The reason is that they are very heavily involved in research, and then many well-known people in academia have worked for Cplex before. Okay, and now what actually supersedes Cplex is Groovy. So there are three people, Zonghao Gu, Edward Rothberg, and Robert Bixby. You can find his name here. He was the founder of Cplex as well. So they founded Groovy, right? So and then the reason they named Groovy is because of their last names. Right? They just took the last name of the three founders to found Groovy. So far, Groovy is still one of the best performing MIP solvers in the middleman benchmark. Until I think maybe 1 or 2 years ago, they stopped participating in the middleman benchmark anymore. Okay, so now if you check the middleman benchmark, there is no Groovy listed there. But then up until they were still participating, they were one of the best performing solver. So in this lecture, I will base the discussion on how Groovy and Cplex work. Right? Groovy is very similar to Cplex because the three founders used to work for Cplex, and then when they started a new company, they sort of inherited what they did before. Now, what can Groovy solve now? It can now solve non-convex mixed integer quadratic constraint quadratic programs. And start from version 11, that was last year, they can solve simple mixed integer nonlinear programs, meaning that you can have very simple nonlinear functions. But starting from version 12, which was released about half a year ago, now they can solve general mixed integer nonlinear programming. We haven't talked about mixed integer nonlinear programming, but it doesn't prevent you from understanding this lecture because in this lecture we will just focus on mixed integer linear programming. Okay. So what's inside the box of the solver? You have already used Groovy, hopefully already in Pyomo to solve some optimization problems. So these are the things I will cover for Groovy. Okay. So it involves what is called pre-processing, cutting planes, heuristics, branch and bound, callbacks. So these are the different things inside the box I will cover. There are some additional things inside the box I don't have the time to cover, right? So if you are curious, you can read their whole documentation to see what's inside the box. But sometimes they have some commercial secret they won't even tell you in the documentation, okay? And if you go to the documentation, there are hundreds of parameters you can change in order to control all these procedures. We wouldn't talk about those hundreds of parameters. Maybe I will showcase a few parameters so that you get some intuition what those parameters can do, okay? Now, let's talk about pre-processing or pre-solve. We didn't even talk about that in the algorithmic part, right? So the idea of pre-processing is that you have a, let's say, linear program, or you have a mixed integer linear program. Maybe the model the way you formulate the problem is not perfect, meaning that you may have some redundant variables or redundant constraints, right? It is very intuitive to introduce those variables, but mathematically those variables are useless, right? So what pre-solve does is it will help you eliminate those redundant variables and constraints and help you tighten the variable bounds, for example, right? So this is, there are different ways to do that. It's kind of based on logic or based on some very simple heuristic protocol to check. So if you solve a given problem, you will likely to find two lines like this in the log file, right? So it says pre-solve removed this number of rows. The rows will be the constraints, and this number of columns. That's what pre-solve does for you. Okay, it can remove redundant variables and constraints. Now, of course, you can change how aggressive or how much time the solver spent on pre-solve or pre-processing. And in Groovy, there is a parameter to control how much time you spend on pre-solve. So let's go to the, let's see, the documentation here. We are, as you can see here, there is a parameter called pre-solve in Groovy. And you can change the pre-solve level, right? So the default value is -1 here. Actually, the minimum value is -1. The maximum value is 2. And this value has to be integer, right? It says the type is integer here, okay? And if you read this documentation, it says the value of -1 corresponds to an automatic setting. Other options are off, right? So if you specify pre-solve equals to 0, you are turning off the pre-solve. For some special cases, let's say if you want to test the algorithm, you may want to turn off the pre-solve, right? Just make sure your algorithm directly affect the problem setting, rather than the pre-solve can be a black box. You don't know what it does for your algorithm, right? And 1 is conservative, right? You don't spend too much time on pre-solve. 2 means aggressive. You spend a lot of time on pre-solve, right? So the more aggressive application of pre-solve, of course, it will take more time, but then sometimes it can significantly reduce the amount of time to solve the problem. Right? Maybe you spend more time on pre-solve and you spend less time on, let's say, branch and cut and so forth. So the idea is you could control it just by changing those integer number. You can also play with it for your problem and see what happens. Okay. Yeah, that's pre-solve here. Now, there is another major technique. We only spent one lecture on it called cutting planes. Right? The idea of cutting plane is to tighten the linear programming relaxation. In our lecture, we talk about Gomery mixed integer cuts and Schrattel-Gomery cuts. Right? So these are just two different types of cutting planes. But within the solver, there are many different types of cutting planes the solver will add. Right? We didn't even talk about that, but if you are curious, you can read the integer programming textbook. Most of those cuts will be covered there. Right? So it's things like Boolean quadratic, polytope, clique cuts, disjunctive cuts, and so forth. So which cut to add is not a trivial problem. Right? There are many people working on how to add the so-called good cutting planes, right? So that you can tighten the linear programming relaxation faster. So which cuts the solver actually added is their commercial secret, right? You don't really know how they decide which cut to add. But what you can control is there is let's go to this documentation. There is also a parameter specifying the aggressiveness to add cutting planes. So this parameter is called cut. Right? Again, usually the default value is -1. You just let the solver choose, right? Because in Groovy, they have some fine-tuned heuristic to decide how aggressive to add each type of cuts. But you can change it as well, right? So if you change this value to 0, you shut off cutting planes. Right? You see, for example, if you're curious, what would a pure branch and bound algorithm gives you, right? You don't really want to solve it using cutting planes. You can specify this as 0. And 1 means moderate cut generation. 2 is aggressive cut generation. 3 for very aggressive cut generation. So how aggressive is very aggressive? They didn't tell you, but at least they are integer levels of values you can choose, right? And then on the right-hand side of this page, you can find there is a whole list of parameters you can change in Groovy, right? As I said, there are hundreds of parameters you can change. You may want to take a look at this, right? Some of these might be interesting, right? So for example, if you click on, let's say, click cuts, right? So instead of a global parameter to control the aggressiveness of adding cutting planes, you can control each type of cutting plane separately. Right? So for some of the problem, if you know those problems very well, you know that this type of cuts could be very effective for this particular problem, then you can make this particular cut more aggressive. Yes?
So in a lot of machine learning techniques, there's like hyperparameter optimization, there's like systematic ways to go through and find the best hyperparameters.
Yes.
Do you recommend doing that for solvers like this where there's so many hyperparameters, or do you recommend using the defaults and only changing what you know you should change?
Yeah, that's a very good question. I would say just use the default if your goal is just to solve one application. And if you know that application very well, for example, if you know some applications where click cuts can be so effective, then you can change that. That is mainly knowledge-based. But there are actually people working on the opposite of what you said, is use machine learning to predict what will be the best hyperparameters for a given instance. Okay, if you have an instance, you don't know what is the best hyperparameter. If you want to tune that, that is like a derivative-free optimization problem. Can be very difficult to solve. But then if you have a very nice algorithm selector, let's say, right? So you could select the hyperparameters that works best for your instance. Yeah. All right, so I won't go to the details of cutting planes since we didn't talk much about that there. So I would want to spend some time on heuristics since we've never talked about heuristics in this lecture before, right? So there are different heuristics implemented in a MIP solver, including neighborhood search, local branching, and so forth. And similarly, you can control how much time the solver spends on heuristics. I think there could be separate parameters for each type of heuristics the solver uses. But I would like to show you a few examples of heuristics, right? Because since we are talking about solving the problem in global optimality, a lot of time has been spent on getting the right bound rather than getting good feasible solution. So I will spend a few slides on how to get good feasible solution. So a simple heuristic is called neighborhood search. This heuristic only applies for general integer variables, meaning that if you have some integer variable between 0 and 10, this type of method will apply. But if you have pure binary variable, this method will not apply. So you will see that in a second. So let's say X star is a solution of the linear programming relaxation, right? Now, what we will do is we will explore a neighborhood that is lower bounded by the floor of X star and the ceiling of X star, right? In other words, you find the LP relaxation, you know that a global optimal solution could be very close to the LP relaxation, right? So then let's just search a small neighborhood around this LP relaxation solution. Right? In this case, you will need to solve so-called a sub-MIP, right? Because you just add some additional bound constraints to the original problem and solve a MIP where the feasible region is much smaller. Right? If you have a general integer variable, let's say from 1 to 10, you probably want to, let's say the LP relaxation is 4.5, then you constrain this integer variable to be between 4 and 5 and solve another integer program. Right? So this should be very, very intuitive for you. Now, a less trivial heuristic is called so-called local branching. This can be applied to mixed integer linear programs with just binary variables. So before looking at the math, the idea of local branching is also neighborhood search. Okay. So the high-level idea is, now I find a feasible solution already, right? So the idea is, if I have a feasible solution to a mixed integer binary program, my guess is that there might be another good solution very close to the current solution I have, right? So how do you describe, a binary solution is very close to a solution I already have, right? So then you need to you need to define some sort of neighborhood. Okay. The way we define the neighborhood is the following. Okay, so now I will show you some math. The idea is we will define a neighborhood such that if you compare two solutions, their binary variables differ by at most k. Right? So let's say if the problem have 10 binary variables, right? And I want to find a neighborhood of this binary variable, I would say the binary variable can only be different from this binary variable in 3 out of the 10 binary variables you have, right? So how do you describe that in math? Okay, so let's assume the set S being the variables that are equal to 1 in my current solution. So S are let's say the binary variables being 1, right? So I will define I, the capital I being the set of all the binary variables, right? So the difference of S, I and S are the binary variables being 0 in my current solution. Okay. Now I define a neighborhood like this. Okay. So let's take a look at this this constraint. What exactly it means here. Right. So this is the sum over all the binary variables equal to 1 in my original solution. These are the sum over binary variables equal to 0 in my original solution, right? And then I say they must be less than or equal to k. Okay. Well, what does this constraint give you? Okay, so what it gives you is all the solutions that is different from the original solution in less than or equal to k binary variables. Okay, so if you write this as Okay, so let's first plug into the original solution, right? So if I plug into x equals to x hat, what will be the level? What will be the value of this left-hand side?
0.
It's 0, right? Because in x hat, all the j in set S equals to 1, so all these are 0, and the j's that in this set I not in S would be 0, right? So x equals to x hat is, this part will be 0 when x equals to x hat, right? Now, if you look at the left-hand side, whenever one of the binary variable changes compared with the original x hat, it will add 1 to the left-hand side, right? So if let's say one of these xj's change from 1 to 0, then this term becomes 1, right? So if you consider all the left-hand side, it essentially gives you the perturbations compared with x hat, right? So that's why it defines, it's like a k-neighborhood of the original solution x hat. Right? So this is known as a local branching constraint. Right? So you can construct a neighborhood with the original solution here. And you can also use this local branching constraint in a branch and bound, where the left branch is saying I'm in a neighborhood differs from the original solution by less than or equal to k, and the right branch is we differ from the original solution by greater than or equal to k plus 1. Right? So that is also a way of doing branching. Okay. Overall, local branching is like a neighborhood search heuristic as well. Right? You constrain that to a k-opt neighborhood. Now, there's another heuristic called relaxation-induced neighborhood search. This idea is much simpler. Okay, so let's just assume you got an incumbent solution. By incumbent solution, it means a feasible solution to the original problem. Right? So this is x bar. And then if you solve a continuous relaxation, in this case, the linear programming relaxation, you got the solution x tilde. Right? And then one is a feasible solution, one is the solution to a continuous relaxation. Now let's compare all the binary variables in these two solutions, and we will fix them if they got the same value in the relaxed solution and in the incumbent solution. Then let's solve the associated MILP and see if we can find a binary solution. Okay. The intuition is that if you have an incumbent solution and then if you have a continuous solution as well, if they agree with each other on some of the binary variables, intuitively you would believe those binary variables can be fixed since they agree with each other. So let's just fix those binary variables. And suppose they agree on many of the binary variables, then there are some additional binary variable you want to search. Right? So you will fix some of the variables that agree with each other and solve the rest of the problem. And mathematically, this can be formulated as this problem. Right? So suppose you are solving a mixed integer program, C transpose x, ax less than or equal to b. And then you just fix the binary variables or integer variables to x tilde if these two solutions agree with each other. Then you just fix those binary variables. And now you are solving a problem with smaller size, right? Because you hopefully fix a huge chunk of those variables. And then there is another idea called solution polishing. The idea is, let's say if you have some good feasible solutions, or hopefully a set of good feasible solutions, you could polish those solutions by using heuristics like a genetic algorithm. That was what reported in this paper by Rothberg, right? So you may recognize name. He's one of the founders of Groovy, right? So the idea of genetic algorithm, probably you have heard about before, is you do some mutation and combining solutions from different MIPS, right? If you have a huge set of solutions, you can perform some heuristics on those solutions. Hopefully, by combining them, you get an even better solution. Sometimes it also requires solving some sub-MIPs. Okay, so now let me talk about this is probably the last heuristic I would like to talk about, called feasibility pump. Okay, again, before looking at the math, let's talk about the intuition of this problem, right? Now, in solving a mixed integer linear programming problem, there are essentially two sets of constraints. One set of the constraints are the linear constraint, ax less than or equal to b, right? And then the other set of the constraints are the integrality constraints, right? So if you remove any of these two sets of constraints, solving the problem is very easy, right? If you remove the integrality constraints, just solving the ax less than or equal to b, it's a linear program, right? It's very, very easy. And then if you remove the linear constraints, just enforce the integrality constraint, it's also very easy, right? If you give me any solution, I can do a very simple rounding to satisfy the integrality constraints, right? So then the idea is satisfying any of these two sets constraints are easy, right, respectively. But then if you put them together, it's very hard, right? Now, feasibility pump means it sort of gives you an alternating scheme to satisfy both sets of the constraint. It first tries to satisfy the integrality constraints, and then after you satisfy the integrality constraint, the linear inequalities may be violated, right? So now let's make the solution satisfy the linear inequalities. And after you make the solution satisfy the linear inequalities, the integrality constraint may be violated again, right? So then you do a rounding to make it satisfy integrality constraint, and you keep iterating between these two schemes, right? So that's why some people treat feasibility pump as an alternating projection scheme, right? You first project onto the integrality constraints, then you project on the linear inequality constraints. Okay, so mathematically, after you understand the intuition, it's quite simple, okay? So we start from a solution x0 that we are in P, where P denotes the linear programming relaxation, right? So if x0 just satisfies the linear programming relaxation, it may not satisfy the integrality constraint, right? But then you can always do a rounding to make it satisfy the linear inequality constraint. That's called this x hat, right? So here we did nothing but let's round out the fractional variables in x0. Now, after rounding, x hat may not satisfy the linear inequality constraint anymore. So what we will do is we will look for a point x1 hat that is as close as possible to x0 hat, but make sure the new point you get satisfy the linear inequality constraint, right? So this is a projection where you make it satisfy linear inequality, right? So if you put this distance, the delta is like so some sort of distance metric. For example, it can be some norm, like 2 norm or 1 norm, right? After this projection step, x hat 1 will satisfy the linear inequalities, but it does not guarantee it will satisfy the integer constraint, right? So then you do a rounding again and keep iterating between these two steps. Okay. From a geometric point of view, this is like what is called an alternating projection algorithm, right? So it's like you have, let's say you have two sets, right? So this is the first set. This is a second set, right? And then I want a point to be in the intersection of the two sets. So that will be this particular region here, right? So in order to project a point to the intersection of the two sets, what I can do is I first project the point to to this black set, right? Now it doesn't satisfy the second constraint. Then I project to the red set, right? And then I keep iterating until it converges to the region denoted in green, right? So intuitively, you recognize for this picture I put there, this alternating projection will converge, all right? Actually, alternating projection will converge when the two sets are convex. Okay, so this alternating projection converge when okay. Now, does alternating projection converge when I have a mixed integer linear program? Or in other words, does feasibility pump converge? Right. So the conclusion is feasibility pump does not necessarily converge, right? Because the integer set is not a convex set. Right. The LP set is a convex set. Heuristically, it works well in practice. Okay, usually after a few iterations, you can find a feasible solution. Okay. Now that's all I want to talk about for the heuristics. Any questions so far? Okay. Now the other thing I've talked about before is so-called branching priority. Right? So in some of the applications, when you are using a branch and bound algorithm, you know it's better to first branch on some of the variables than the other set of the variables. Things like if you, in a scheduling problem, you want to first branch on the assignment of jobs to machines before you branch on the sequence of the jobs on a given machine, right? Because after some of the variables are branched on, a huge chunk of the rest of the variable will be fixed, right? So in those cases, you want to change the branching priority for the solver. Otherwise, the solver will use its own heuristic to decide branching priority. Okay, so another thing is called solution pool. In some of the problem, you may want to get multiple solutions from an MILP instead of just one single solution. This happens a lot in practice because the solution you got might be, for example, very counterintuitive to the practitioner. Right? Even though you got optimal solution, it's very hard to interpret that optimal solution. Then someone may prefer a suboptimal solution, although it's not global optimal, it might be easier to implement in practice. Right? So in that case, you would like to get multiple solutions in MLP. So this is so-called solution pool, where the solver will give you all the feasible solution it found during branch and bound. But it is different than all the feasible solutions to the original problem, because branch and bound is sort of problem dependent, right? It does not give you all the feasible solutions. Some of the nodes may be fathomed by optimality, but it still has some good solutions there, right? But there are some other solvers, if you wish to find all the feasible solution, it will give you. But I don't think Groovy or Staplex can give you that. You can read the documentation to see if I was wrong. Okay, so I will like to talk a little bit about multi-objective optimization. So in some of the problems, you may have different objectives you want to optimize. Right? Let's say if you design a chemical plant, right? You can have two objectives. One is let's say the cost of the chemical plant. The other is CO2 emission of the plant. Right? So these two might be two conflicting objectives. Right? You cannot improve one objective without sacrificing the other. Right? So in that case, what people typically do is to find what is so-called a Pareto optimal. Okay, so the Pareto optimal can be found by let's say you have n objective functions, you can take a convex combination of those n objective functions, right? Lambda is a weight you assigned to a given objective, right? Now, how do you decide the weights, right? So then it's really up to you which objective you really like, right? If you just want to minimize one of the objectives, then you put weight 1 on one of the objectives and 0 on all the rest, right? But then if you want to find some trade-off, you can change the weights and see what happens, right? So that probably can give you some idea of making decisions in your real life, right? I find many people struggle to make decisions in their life just because they are trying to minimize 10 objectives at the same time, right? But you should be aware because of the constraints you have, you cannot minimize all the 10 objectives at the same time. You have to sacrifice something, right? So you can only find a Pareto optimal in such case. It just different people should assign different lambda values to their different objectives, right? Okay. Now, let's talk a little bit about linear programming algorithm. I've talked about this briefly before, right? So in the solver, there are 3 or 4 different algorithms to solve linear programs, right? If you're just solving a linear program, you can pick one of these algorithms, right? Including primal simplex, dual simplex, and barrier method, right? Does anyone still remember what's the difference in the solution if you use simplex algorithm versus using barrier algorithm? Yeah, this is a very good exam question, by the way.
Do you mean how it works?
Yeah, so it means the type of solution you got from those methods. Huh? Oh, yeah, exactly. Yeah. Right. Yeah, so for the simplex algorithm, the solution is guaranteed to be an extreme point or a vertex, right? For barrier algorithm, there is no guarantee of that, right? Unimodel. Not really. It's just you know, in simplex algorithm, you deal with a basic feasible solution, right? And in barrier, you are using this log barrier method to solve that problem, right? So it will, as long as it satisfies the primal and dual feasibility tolerance, the methods will terminate. It may not be at a basic feasible solution. Okay. Yeah. Then the crossover, again, the crossover means it will push a barrier solution to an extreme point. Okay, so if you choose barrier without crossover, it will give you a problem with many decimal places. And if you choose barrier with crossover, you will still end up with an extreme point. You use some method to make sure it's an extreme point. Right? So if I'm just solving an LP and doesn't care whether it's an extreme point or not, you should just use barrier without crossover. Usually it's the fastest. Now, if you are solving an MILP, I don't think changing the algorithm helps a lot. Maybe help a little bit, but at the end of the day, the root node relaxation has to return an extreme point. The reason is after solving the root node relaxation, and then you start doing branch and bound, it will use dual simplex to warm start the branch and bound, right? Because after you add some branching constraint, x less than equal to 0, x greater than equal to 1, the feasible region of the dual will not be changed, right? So the dual feasible solution at the root node is still dual feasible at the child nodes, right, after you branch. Right? So the dual simplex is a very good algorithm amenable to warm start, right? So that's why it has to be an extreme point if you are solving an MILP. Now another thing is parallel computing. It is very easy to see branch and bound can be easily parallelized, right? If you have a bunch of leaf nodes, you can solve all of them at the same time. By default, if you have, let's say, a server with hundreds of threads, by default, Groovy will use all the threads on your machine. But sometimes it can be counterproductive. Empirically, using 6 to 8 threads gives you the best performance. That means sometimes using more threads can be counterproductive. Right? They are, I don't know the exact reason. Maybe there are interference between the threads, or there could be communication overhead that makes the problem counterproductive. Probably we need a parallel computing expert to really tell the reason. But empirically, I heard, so if you even if you have a server with hundreds of threads, change the threads number to 6 or 8. It will usually give you good performance. Yes?
Is that irrespective of like computing power?
Right. Okay, so let's say if your research group is really rich and then you have a very good computer, still don't use all the threads. You could play with it and see what happens, right? But that's what usually people tell me.
So you need the thread on the core.
Yeah, so usually in most of the machines, one core gives you 2 threads, right? So if you have 48 core, that it means 96 threads. Okay, you can just specify 8 threads, or you can gradually increase it and see what happens. There are also solver APIs. So what does APIs mean here? Well, all the MIP solvers are usually written in compiling language like C, right? But nowadays, how many people write programs in C? I mean, or you writing Fortran? Okay, good for you. even better. Okay, yeah. So so I guess most of the people haven't written programs in C for a long time, and then there are languages that are easier to write than C or C++. Maybe you prefer to use like Python or MATLAB, right? What the API does is like if you want to talk to the solver, right? The original code was written in C, but then you want to talk to the solver in Python, right? So then there are different functions or APIs you can use to interfere with the solver, right? So maybe you want to change things like the branching strategy and so forth. There are corresponding functions in Python you could use. Yeah, then I want to tell you a little bit about how PyOmo works, right? You have been using PyOmo for a while, but then how does PyOmo talk to different solvers, right? As I said, all the source code of the solvers are written in C, right? At the end of the day, the solver has to receive the model in some way, right? So there are a few different ways PyOmo can talk to the solvers. One is through so-called the LP file. So LP file is a file format to save a mixed integer programming model or a linear programming model on your hard drive. Okay, so it is a file format just like TXT or PDF, right? But LP file is a specific file format to save mixed integer programming models, right? So what PyOmo can do is you have already written a PyOmo model, and now PyOmo can convert your model into an LP file, right? Then the solver can read that LP file because the LP file is sort of a common language among different solvers, right? So you can load that LP file and solve that, then return the result back to you. Okay. But that requires saving the LP file on your hard drive, right? And then it read again, right? There is another way to communicate with the solver by using their Python API, right? So from the previous slides, I said there are different programming language you can use to talk to a solver, right? You can use Python to talk to a solver. But of course, for different solvers, they have different Python interface, right? So PyOmo actually built some interface to talk to different solvers using their Python API, right? So that is called Groovy or Cplex persistent interface. Okay, so it is a way of talking to a solver using their Pyomo API, right? Yeah. And you can check how this work by checking maybe the Groovy persistent.py. Right? Similarly, you can imagine there is a Cplex persistent.py as well, right? Since Cplex and Groovy use different Python API, in order for Pyomo to talk to them respectively, you need to implement this wrapper for these two solvers respectively as well. Okay. Yeah, so it's easier if you read this piece of code than I just talk about. But here, at least from this slide, you know these things do exist. If you get into that, you could read the source code. Now I would like to talk a little bit about the callback or lazy constraints. So we talked about lazy constraint before in this subtour elimination constraints, right? The motivation of lazy callback is for some of the applications, like traveling salesman problem, there can be exponentially many constraints. So even though there are exponentially number of constraints, we know that only a very small subset of them are active at the optimal solution. Right? So therefore, you do not want to throw all these exponential number of constraints at the beginning. It will slow down solving even the LP relaxation. Right? So the idea of lazy callback is you will add these constraints only when needed, right? So that's why we say those constraints are lazy. They will not show up until you find out they are necessary, okay? So when you find they are necessary is at some of the branch and bound node, you may find a solution. You may find a feasible solution, right? But then you have not added those lazy constraints. And if this feasible solution violate any of those lazy constraints, you will add those constraints back to the problem. Right? So they are added on the fly during branch and bound. Only added when you find out your current solution violate those lazy constraints. Okay. And those lazy callbacks are useful in some of the algorithms. We haven't talked about this algorithm before, but we will talk about them in the second half of this semester. So for the project, as I said, there are two types of project we offer. One is application, the other is algorithm implementation. Right? You can consider implementing this algorithm like single tree Bender's decomposition or single tree outer approximation. If you are interested in that, we can talk about them more after next lecture. Okay. The other type of callback is so-called cut callback. Okay. So the difference between cut callback and lazy callback is the following. All the lazy constraints are necessary to make sure the solutions are optimal, like the subtour elimination constraints. You have to make sure all the subtour elimination constraints are satisfied in order to certify a solution is optimal. Okay. But you know that most of them are redundant, but at the end of the day, you have to make sure all of them are satisfied for the solution to be optimal. The difference between lazy constraint and user cut constraint is user cut constraint is not necessary. Right? So user cut constraint is not necessary in the sense that if you add them, it may help you solve the problem faster. Right? For example, you may know some cutting planes the solver doesn't know. Right? But you know after adding those cutting planes, you can solve the problem faster. Right? But you don't need those cutting planes to solve the problem to optimality. Right? Even without the cutting planes, you do a very naive branch and bound, you will find the solution anyways. Right? But you know that those will help the solver solve the problem faster. So this is called the user cut callback. Right? The idea is when you encounter, let's say, some relaxed solution, and after adding those cut, hopefully you can make the relaxation stronger, right? To reduce the number of nodes in your branch and bound. Okay. Now it comes to the most important thing I would like to cover, which is how do you rate the solver log file, right? So typically when students start working on some mixed integer linear programming problem, they ignore the log file of the solver and just say if I got a solution or not from the solver. Let's check if Palmo gave me an optimal solution or not, right? And then I just check the solutions. But then you should, one takeaway from this lecture is each time you solve a non-trivial problem, right? If you solve a problem that can be solved in 1 minute, then you don't really need to care about the log file, right? But for meaningful problems, usually it cannot be solved very easily. You should, every time you solve those problems, you should read the log file and see what's happening here. Right? Make sure you save the log file each time you solve a problem. Now, I want to show you how to read a solver log file. Okay, so this is an example log file we got. Okay, now again here, if you look at the start of the log file, it tells you the number of threads you have on this machine. In this case, we have 48 cores and 96 threads, right? And then here, because we specified we are only using 8 threads, right? Because I told you usually using 8 threads is a good number, okay? Now, it will first tell you the size of the model, right? The number of constraints, the number of rows, the number of columns are the number of variables, and the number of non-zeros in the problem, okay? And it also tells you the types of the variables. You have this many continuous variables, this many integer variables, right? If I'm writing a paper and then you want to benchmark an algorithm, you should write down all those statistics in your paper. Okay, these are the number of variables you have. So what matters a lot is this coefficient statistics. Okay, so it will tell you the matrix range, right? So if you have a problem, let's say AX less than or equal to B, maybe minimize C transpose X. So the matrix range is a range of parameters in this A matrix, right? You want to make sure this matrix is very well scaled, right? Because all the mixed integer linear programming algorithm has to take a matrix inverse anyways, right? If this matrix is not very well scaled, for example, if you have a number 1e raised to the power of -8, and here you have some big numbers. We can keep pointing toward a big number, right? So if you have a very small number in a matrix range, it is very difficult for matrix inverse, right? Because the solver also has a numerical precision. You cannot assume the solver have 10 to the power -40 precision. Actually, if you check the numerical tolerance, it's usually 10 raised to the power of -5 or -6, right? So that's, make sure if you divide these two numbers, it's in the range of 10 to the power 5 at most, right? Then you will not have numerical issue. But it's better if you keep the range as small as possible. Okay, and then here you have objective range. That will be the range of C, and you also have the range of B, right? So here, this is the bounds of the problem, and the right-hand side range is the range of B. Here, clearly, I have a very big number on the right-hand side, right? So it looks very suspicious. Very likely, I have a very bad big M value that gave rise to this number, right? So you should, if you see those numbers, you should be suspicious of, let's say, big M values, and then you should make this right-hand side smaller. Yes?
So you said that for the matrix range, we want it to be kind of at most a range of 10 to the 5th.
Yeah.
does that apply for the objective and right-hand side ranges as well?
Yeah, so that's a good point. I would suggest you do that, try to do that if you can. But I would say the algorithms are less sensitive to the objective and right-hand side because you are not taking a matrix inverse on the right-hand side, right? But maybe their range still will affect you. I would also try to make those as small as possible, right? But the matrix range is very important. Okay. Yeah, so each time you solve a problem, you should check those ranges to see if you made some mistakes in your data, right? If all the range are nice, then likely you are doing a good job. Right? So now it says it finds a heuristic solution with this objective. So perhaps it already ran some heuristic. Now it will run pre-solve, right? Pre-solve will remove this number of constraints, this number of variables. And after the pre-solve, you can see the number got reduced very significantly, right? Because if you check here, the pre-solve problem are only left with around 2,000 binary variables, right? Initially, we have around 20,000 binary variables, okay? Yeah. Now, after that, it will run the algorithm to solve the root node relaxation. So in this case, it was using the barrier algorithm. You should also be careful about those statistics. Okay. Sometimes when things go wrong, it will give you a warning for those barrier statistics. But in this case, it looks like it is all right. So if you solve the barrier algorithm, because since it's a primal dual type of algorithm, it gives you the primal objective and the dual objective. Okay, now it says the barrier solves the problem in 31 iterations. Okay, now it's like the root node relaxation has been solved, right? So after the root node relaxation has been solved, it will give you the objective value of the root node relaxation. That's something to check as well, right? Because the root node relaxation can tell you whether this problem has good relaxation or not. Okay, so now it starts doing branch and cut. Yes?
Sorry, when you say that the root relaxation, how do we read that to know if it's doing a good job or not?
Oh, yeah. So a good thing to check is more like a post hoc way of doing things, right? You check the root node relaxation, and at the end you could check, let's say, the optimal solution when it terminates. It's relative this number, right? And then you could check how good is the root relaxation compared with the optimal solution to give you a sense of the formulation, how tight the formulation is. Okay. Yeah. Now, it will start doing branch and bound. It will give you here the number of nodes. Okay. As you can see, up until here, the number of nodes is at 0, right? So what it does is the solver will do a lot of job at the root node, trying to do things like tighten the variable bounds or finding good feasible solutions, adding cutting points, okay, at the root node. Now, so this column give you the current node objective, okay, and here it gives you the bounds. With the incumbent solution, which is if you are minimizing the incumbent solution is an upper bound, the best bound is a lower bound, right? And it calculate the gap based on those bounds. And here it gives you the solution time. Okay, so what this H means is the heuristic find a solution when this if this H shows up. Okay. So as you can see, after the root node, the number of nodes will quickly grow. Right? Since once it starts doing branch and bound, the number of nodes will quickly grow. At the end of the day, you can find out it will terminate with around 0.02 percent optimality gap, and these are the upper and lower bound. Okay. And after it terminates, very interesting thing to read is the type of cutting planes the solver have added. So now it says it have added 4 gamma cuts, and then it also have added 3 projected implied bound, 85 mixed integer rounding cuts, and so forth. Okay, and in total it will tell you the number of total number of nodes, the total number of simplex iterations, and give you the best objective and the best bound. So that's roughly the way to read the log file. There are a few things you should pay special attention to, which I outlined in this slide. First bullet point is check the matrix range. Right? If the matrix range is bad, you will encounter numerical issues. And usually, easy problem can be solved very fast without doing much branch and bound. And hard problems usually consumes a lot of memory. Once it starts doing branch and bound, the problem size this tree will explode. You should also check your memory consumption from time to time. Right? If you are using a server, maybe your server will quickly run out of memory. It's very hard to reboot a computer if you run out of the memory on a server. So maybe you could set a memory limit, right? If we exceed the memory limit, it will terminate. Okay. The other thing you want to check carefully is why the problem is so slow to solve. Okay. Sometimes it is because it struggles to find a good feasible solution. So how do you know the solver struggle to find a good feasible solution? From the log file. Or in other words, how do you know the solver already gave a good bound at the beginning?
The size of the gap.
Yeah, so the way you could check is, let me go to this log file here, okay. So if you look at this particular line here, this is a line where the solver hasn't even started doing any branch and bound, right? The number of nodes is 0 here, right? And the bound you find at the root node is this number here, okay? So if this bound does not improve a lot at the end of the day, okay, so if you find out once the solver terminates, it finds the optimal solution, this bound does not improve a lot, right? That means at the root node, you already got a very good bound. The branching does not help at all to improve the bound. Then that means the bottleneck is finding a good feasible solution, right? Because here, as you can see, the feasible solution at the root node is very bad. Then you should spend more effort on trying to design some heuristic to help the solver find a good feasible solution if the bound is already pretty good at the root node. Right? On the other hand, for some of the problems at the root node, maybe the solver already find the best solution. And then the rest of the time is spent on branching. Right? So then you should think about adding more cuts or finding a tighter relaxation. Right? So that's a way to distinguish why the solver struggles. Sometimes the solver struggles at both finding a feasible solution and closing the gap. Right? And then you need to do both things. Okay, so that's that. Then let me just go over this again of numerical issues, right? Because many students always forgot about checking this matrix range, and then the problem was not solved, and they didn't know what's going on, right? So here, again, the first thing is skill, right? Here, if you have a matrix range that is too large, one thing you could do is use this parameter called numeric focus. It will give you higher numeric precision. But that's not recommended because that will slow down the process. You should try to reformulate the model to make this range small. They are usually for most of the problem, you should be able to make this range small. Okay. And then do not write something like 0.333, right? If you want to write 1/3, just multiply the constraint with 3. Do not write this type of number. It will give you a round-off error. Okay, the other thing is you could get a wrong answer with a very big M. Okay, so this is a big M constraint, right? X is binary, Y is continuous, and you have a very large big M. So the thing with this large big M is not just you will have a big relaxation gap. It will also give you a solution that is integer infeasible. So here, it could give you a solution where X is 0.0000999, right? And Y is 9.999. And it will report this solution is integer feasible. The reason is there is an integer feasibility tolerance. So the solver will not always guarantee all the numbers are exactly 0 or 1. There is a feasibility tolerance you set. As long as a number is 10 raised to the power of -5, it will treat this number as 0. Okay, so it will not continue branching on it. Otherwise, you have to branch on all the variables, basically. Right? So that's why the solver will not do that. So if you have a large big M, this numeric solution will sort of cheat, right? So it will give you a very small number on X and treat X as 0, but here you still have a non-zero Y. That's not the logic you want to enforce here. Okay. Yeah, so then the other thing is to check the log file for warnings, right? So it will give you warnings during optimization. For example, it will give you things like the tolerance is tightened. This typically means you have a very bad scaling in your problem. Okay, and then at the end of the day, it will also tell you things like if you have the max integrality violation exceeds tolerance, right? So this will be a good sign that you will have very large big M's in your problem. That's why you have a max integrality violation exceed the tolerance. And then there are other things as well, right? So sometimes it will even tell you this is possibly due to a large matrix coefficient range, right? So again, make sure you have good matrix coefficient range. Now these are all the references I have. You should check some of those documentations if you are interested. Cplex has a user manual. Of course, Groovy has a documentation. For beginners, you could check the Groovy YouTube channel. Sometimes they have very good seminar series, not just on tutorials, but on the recent development. For example, recently they have like a GPU solver. You could take a look. And then if you want to read a bit more about user cuts and lazy constraints, there is a very nice blog by Paul Rubin I would highly recommend. I also took some slides from, I think they are from Groovy, modeling best practices and techniques related to how to scale the variables and so forth. Okay.